Hello guys, welcome to my channel. Let us assume today we gonna solve some problem of real number sequence from the exercise 7 of SK Mapa's real analysis book. Okay, so let's start. The first question is, give an example of a sequence of rational numbers that converges to an irrational number. Okay, so we have to find the sequence of rational number which converges to a irrational number. So let's start. If we take the sequence 1 plus 1 by n whole to the power n, the sequence is, we put 1 2 to the power 1 plus whole square and so on and so on. So we can easily see that this is the sequence of rational number, but the sequence converges to E, which is an irrational number. So this is the example of the first question, that is the sequence 1 plus 1 by n whole to the power n is the sequence of rational number which converges to a irrational number, since E is an irrational number. Okay, now we gonna move to the second question. Give an example of a sequence of irrational number that converges to a rational number. Okay, so the opposite of the first question. Here we take the example. This is the sequence. We can easily see that since root 5 is the irrational number, so we can say this is the sequence of irrational number. Let's see its limit. Its limit is 1. Okay, so this is converges to a rational number. So this is the example of an sequence which of irrational number which is converges to a rational number. Okay, you can take any irrational number like root 2, root 7 or anything. Okay. Okay, now quickly move on to the third question, which is let un be a bounded sequence and limit vn is equal to 0. Then we have to prove that un and vn is equal to 0. After this, we have to utilize this result to prove the following three questions, following three sequences convergence to 0. Okay, so let's start. Let first prove the upper portion, and that is limit un vn is equal to 0, where un is a bounded sequence and vn is converges to 0. Okay, so prove, since un is bounded, since un is a bounded sequence, so from the definition of bounded sequence we can write un is lesser equal to some capital M which is a natural number for all n belongs to capital N. Okay, since un is a bounded sequence, and since limit Vn is equal to 0, we can write from the definition of a limit of a sequence for epsilon greater than 0, there exists k such that mod of Vn minus 0 less than epsilon by n for all n greater equal to k. Okay, so from un, because un is a bounded sequence, we can write mod of un is less or equal to n for all n belongs to capital N, and since limit Vn is equal to 0 for or epsilon, for p assigned epsilon greater than 0, we can write there exists a k belongs to n, the set of natural number such that limit mod of Vn minus 0 less than epsilon by n for all n belong greater equal to k. So un mod of un into Vn is equal to lesser, we can write lesser equal to m into mod of Vn, okay, for all n belongs to capital N, and since Vn is lesser equal to k, epsilon by m for all n greater equal to k, so we can write again mod of un into Vn lesser equal to m into epsilon by m for all n belongs to k, for all n greater equal to k. Okay, so we can write un into Vn lesser equal to epsilon for all n greater equal to k. So from the definition, from this we can say, from the definition of the limit of a sequence, that limit un Vn is equal to 0. That is the proof. Okay, we have a proof that the limit un is Vn is equal to 0 whenever un is a bounded sequence and Vn is a sequence converging to 0. So for this, firstly we use the definition of bounded sequence, that is un mod of un is lesser equal to m for all n belongs to capital N, and then we use the definition of the limit of a sequence, that from the definition of a limit of a sequence we can say, for a pre-assigned positive epsilon there exists a k such that mod of un into Vn lesser equal to mod of Vn lesser equal to epsilon by m less than epsilon by n for all n belong greater equal to k1, and using these two results we can see that mod of un Vn lesser equal to epsilon for all n greater equal to k, again from the definition of the limit of a sequence we can say limit un Vn is equal to 0. Now we will prove the following result using the above result. So for the first case, Number 1, sin n. The sequence sin n is a bounded sequence and limit 1 by n is equal to 0. N tends to, obviously limit is n tends to infinity, 1 by n is equal to 0. So their product is also, the limit of their product is also 0 using the above result. So we can, so here un is sin n and vn is 1 by n. So limit un vn is equal to 0, that is limit sin n by n is equal to 0. Okay, clear? If you have any question, ask me in the comment section. Number 2, here we take un is equal to 1 by n whole to the power n and vn is equal to n by n square plus 1. Okay, now we can easily see that un, this sequence is bounded since all its element is either minus 1 or 1. Okay, so we can say that this sequence is bounded, and now we will check limit vn is equal to 0 or not. Limit vn is equal to n by n square plus 1, easily it is a infinity by infinity form, so we will differentiate, so that will give the answer 0 from L'Hospital rule. So limit un vn is equal to 0 from the above result. So now we quickly move on to the third question. In this case, we will take un is equal to minus 1 whole to the power n and vn is equal to an. So since vn is limit vn is equal to 0, whenever limit vn is equal to 0, then the product will be 0 from the above result, and since un is clearly the bounded sequence. Okay, thank you. If you have any question or any doubt, ask me in the comment section.